Part of what we are actually expecting out of the differential approximate method. It really all lies in the following big idea, which is that when you force your terms into a d-finite form, then the asymptotics of the d-finite form are an approximate for the asymptotics of your unknown generating function. Now, there's no reason a priori why this should be true. Right? For example, if I tried to predict something about the sequence that starts 2 to the n for n less than 1,000,000 and 3 to the n bigger than that, you could give it the first 900,000 terms and it's not going to predict what happens. But amazingly, for our nice combinatorial problems that come up all over the place, when you force your terms to fit to a d-finite form, you get remarkably good approximations for the true unknown generating function. And we can verify that this works because we can try to do this with sequences where we know the true behavior, and we see that it matches up very well. Okay, so let me talk about fitting to d-finite forms, so you know what I mean there. What I mean by fitting is first pick a d-finite, I'll call it a d-finite model. So pick a differential order. Maybe you want to do a third order, second order. And pick degrees for the polynomial coefficients. Maybe it would be better to call it a template instead of a model. You pick the differential order, degrees for the polynomial coefficients, and then you perform an algorithm kind of like what GFUN does. For now, I just want to treat it like a black box because I don't have time to go into the details. But you pass into the algorithm some number of terms, depending on the template. And what you get back is a d-finite generating function that matches the terms you gave it exactly, and then probably goes wrong after that. So it matches the given terms. So what GFUN does is it gives this algorithm some terms and also gives it some extra terms and says if you can guess something with 20 terms and then it matches the next 10 I've given you, it's probably correct. We are ignoring the next 10 terms. We're giving it just enough to form a guess, but no extra tolerance terms to see if its guess is actually right. For an example,
you're never going to use these squares, right? I mean, you could.
No, it sets up a linear system basically and solves it. Or another idea which is slightly faster algorithmically is something called Hermite approximates. Yeah. So let me show you an example that you get with our running example. With the template for a d-finite function that's a first order, so we've got p1 of z, f prime of z, plus p0 of z, f of z, plus an inhomogeneous term equals 0. And let's say that all the degrees are 2. So we've basically set up a template here. There are really 9 unknowns. It's the 3 coefficients from each one of the polynomials, and I'm sweeping some information under the rug. But if you feed this the first 9 terms of your sequence, here's what it returns as a guess. Okay, so I don't want to write that on the board, so I put it on there. It's a d-finite function. It matches our template. And when you find the series expansion of f of z, I'm going to show you what we get. The series expansion of the solution of that linear differential equation starts out just like our sequence, 1 plus z plus 3z squared, all the way up to the correct z to the 8th term. We fed it 9 terms, it gives us back 9 terms correct. But then the next term is some giant rational number, z to the 9th. But it's pretty close. So this rational number is 3399315 approximately, where the correct next term of our sequence was 3399164. Okay, so basically you are giving it some terms, it's giving you back a generating function that matches the ones you gave it, but then probably, almost certainly goes awry afterwards. What's amazing about differential approximates is that even though there's no reason for it to be true, the asymptotics of this are a good approximation for the asymptotics of your real generating function. That's the big idea for differential approximates. Now, past that, it kind of goes into subtleties, because what we don't want to do is take one model and say, well, this is probably our growth rate. We take this giant collection of models that we find by taking a d-finite form and tweaking it a little bit. So maybe we make them all, for example, third-order differential approximates, but we let the polynomials be 20-20-20, or 20-19-20, or 20-21-20. We let them vary by just a little bit. We get a large collection of models that are very similar, but different. So now we have a lot of d-finite models. And we have to find some way to average them together. Now, average is in quotes because that's obviously way more complicated than that. The first thing that you do when you want to find the asymptotics of a d-finite function is you locate the singularities. That tells you the exponential growth rate of the sequence. And that's easy to do with d-finite functions because the only candidates for singularities are the roots of the leading polynomial. So in that case, it would be the roots of p1 of z. So our first step in the method of differential approximates is to take these d-finite models and find all of the singularities of all of them. So for example, if you have 100 d-finite models and each one of them has 100 singularities, now you've got 10,000 singularities and you plot them all on a graph. So here's an example. This is a complex plot. In this case, it's for the sequence that I keep talking about. It's 27 d-finite models for a particular reason, and this is all of their singularities. It uses just the 100 terms, not the whole 1500. It's on the complex plane, and as expected, a lot of them are happening right here near the origin, but Maple just happened to find one at about 55,000, which is kind of a strange place for a singularity to be. When we zoom in here on the origin, we see some more interesting behavior. Again, this is a complex plot, so everything up here has a complex conjugate down here. That's why we have that symmetry. What are we looking for? So I guess the question is, what would we have to see to be convinced that our true generating function has a singularity somewhere? Well, what we would want to see is that all of the models, or maybe most of the models, have a singularity there. Let me show you an example. These points up here, each one of these diamonds is a single singularity. So one of the models has one here, but the other 26 don't. So does our true generating function have a singularity here? Well, probably not. On the other hand, this one point here that's kind of darker, that's darker because it's really 27 diamonds on top of each other. Every single one of the d-finite models has a singularity, not at the exact same point, but very, very close. In a bubble of radius about 2 to the negative 10, I think. All 27 of them have a singularity right here. And so we predict that that means our true generating function has one there as well. I'll get back to that one, but let me zoom in on the origin a little bit more. A lot of this here is noise. It looks like you have a bunch right here, but we're looking for very, very tiny bubbles. So for example, this doesn't register. A lot of this doesn't register. On the other hand, This does. This is 27, all in a very tight bubble, and its complex conjugate is as well. So we expect that our true generating function has complex singularities as well. But the dominant singularity here, the one that's closest to the origin, is found right here in this cluster. So we zoom in on that, and we zoom in again, and this is really the interesting part of our singularity plot. So let me explain what's going on here. We're in a very small window, and it looks like we've got a large number of singularities there. But the picture is actually even better, because this dot right here, this is really 27 singularities in a bubble that's something like 2 to the negative 35 or 2 to the negative 40. A very small window, and every single one of our d-finite models has a singularity there. What all of these other dots is that once you exclude that one, which is really all 27, these other dots are all 27 models having a second singularity in a close window. And this is what I mean about averaging being complicated. If we were to just look at the asymptotics of any one of our models, it would say something like, well, you've got a singularity here, and you've got another one close by. But really, when we see something like this, when we see all of the models having two singularities very close, we say that the models are trying to tell us there's actually a double singularity there, which happens all the time in generating functions. It's a multiple singularity. And this is really the place where we start to do some analysis.
What degree are you looking at?
This example was, I think, third order differential approximate. So second or third, I don't remember. So what the method says is, well, given that they all have one here, and they all have a second one here, I predict that there's a double singularity somewhere at this point. And then what the method has to do, this is just for the mu. This is just for that exponential growth rate. Then when it wants to find the alpha, it has to use the fact that even though for the actual models, they're not double singularities, they are two close but different ones, when it actually goes to compute the alpha, it has to know that we're assuming it's a double singularity. Because if you treat them as two close single ones, you get entirely different asymptotics. It changes the whole picture. So once we do this, if we make the conclusion that it's really a double singularity, we go back and we edit every one of those models to say it's not really two single singularities, it's one double. We edit all the models to reflect that, and then we go back and we work on getting the alpha. And that's really where the method ends at this point. It's only the mu to the n to the alpha that was done in the 70s. Part of this is because they didn't know how to extract the log n to the beta term, and part of it is because they didn't know the full types of asymptotic behavior that d-finite functions could have. For example, they didn't know about this e to the q of n to the gamma term, which lets you have things like 2 to the square root of n. This can happen in some sequences, but the way that they analyze it assumes this doesn't exist. So when you run across a sequence that has this, it fails entirely. So what I'm working on now is combing through these differential equations textbooks from the early 1900s that are about this thick, trying to understand how they do this analysis so I can figure out how to do the proper averaging. Now, I want to go back before I finish.
So this comes in extra, this type of...
This kind of term here? Yeah, absolutely. So for example, Tony Gutman studied 1, 3, 2, 4 avoiding permutations. And if you know permutation patterns, this has been an open question for decades. What do the asymptotics do? We only have 36 terms. And he had some numerical evidence that said it looks like mu to the n, mu1 to the square root of n to the alpha. So it looked like it had this term here, which he called a stretched exponential term. And said, well, d-finite functions can't have that asymptotic, so the differential approximate method fails. Well, in fact, what we saw here is that d-finite functions can do this. We just have to figure out how to do the averaging properly. The models are always telling us what's going on. We just have to know how to read the information from them. So the last thing I want to mention, well, I guess two other things. One is that my guessing program, which will take in known terms and try to guess an exact form, actually did return something for this sequence. But it's not d-finite, it's what we call differentially algebraic. So you can have things like the derivatives being squared or multiplied together. And you get this with about 300 terms. It matches the other 1,200 terms, so it's almost certainly correct. But what do you do with this? Right? We found this and we said, well, okay, now what? It doesn't tell you anything about what's the growth rate, what's the asymptotic behavior, nothing about that. So even when you have exact things, you still want to apply these methods sometimes.
And officially it's proved or rejected?
Well, it's proved.
Yeah.
Yeah, it's experimentally proved.
Okay.
Yeah, exactly. Okay, so the last thing that I want to say about this sequence is another example of what the differential approximate method can do. And so if I go back to these number lines here, I mentioned this singularity at about -3 being very important. And let me show you why. When you perform the differential approximate method with 500 terms in sequence, it estimates the dominant singularity, the one that actually gives us the exponential growth rate, to 0.0749, bunch of stuff, 518, plus or minus 10 to the -17. Now, this is experimental, so this is not a rigorous error bound. Usually when I write something about this in a paper, I take whatever error bound this is, and I multiply it by 10. So I change the -17 to a -16, because in practice, I've never seen an approximate be incorrect when you do this to the bounds. So out of maybe 100 sequences I've checked or something, those error bounds always hold. This is fine, except you can't do anything with this number. You would want to try to see, is it an algebraic number? So you plug it into Wolfram Alpha, or you plug it into the inverse symbolic calculator, and you can't guess what this is. Is it a root of a polynomial? I don't know. But at that other singularity, the method tells you is about -2.88202477916, plus or minus 10 to the -11. And this is something the ratio method can't do, which is tell you about subdominant singularities. But here's something that we found. When you look at the number, -256 over 9 pi squared, this number is -2.882024779159. So this is obviously experimental, but it looks almost certainly like this generating function has a subdominant singularity at a transcendental number. That means it can't be d-finite. So this is just more experimental evidence that tells us we can combine the exact answer with the differential algebraic thing with this experimental evidence and think we have a non-d-finite function. So the differential approximate method can do a lot of interesting stuff. It's currently pretty limited in what it can do, and I'm working on extending that. I hope eventually it'll be a combinatorial tool that is useful to a lot of people. And if you're interested, I have a Maple implementation that I'm happy to send you. Thank you.
Again, we can answer questions in private. If you'd like to join us for dinner, please let me know right now.
I would like to join you for dinner.